All right, so Friday we said we've got these vectors. Vectors are simply a what we call a directed line segment. Um, Basically, any quantity that we want to describe in regards to a length and a direction. Okay, so that vector AB right there, from A to B, um, is a directed line segment. And we talked on Friday that there are things like temperature or mass or volume, age, just certain things that we've been dealing with for our whole lives that can be represented with just one number. Okay, and those we call it scaling. But there are also things that require two components, two values, and something like maybe velocity is speed coupled with a direction. Okay, and that needs a vector to be represented with. Okay, and there's a lot of other things throughout mathematics. Usually, speed and acceleration are two that you deal with a lot in regards to vectors. Um, but we need two components, and then this is what we get with vectors. That's we call that usually. You see here we call it vector U. And we talked about how we can take vector U and just kind of look over here right now. You don't know what this notation is right now with the 5 and the 2, but that is describing the vector algebraically, meaning that if I change the vector, it changes those numbers, right? Okay. But if those numbers don't change, what's it tell me about the vectors? It's the same vector, right? Okay. So this vector here, where it starts at A being 2, 3, is the exact same thing as if that vector started at 0, 0. Does that make sense? Okay. They have the exact same length, no matter where it's at, and it has the exact same direction. Okay. Um, something to see that maybe the direction, that one would be a length of what? 3 radical 2, and it has a direction of 45 degrees. Would you guys agree with that? Right there, it still has a length of 3 radical 2 and a direction of 45 degrees. Okay? Always going to be the same length and direction, okay, no matter where. So because of that, a lot of times it makes it convenient if I'm somewhere out in just two-dimensional space somewhere dealing with vectors, understanding that I can kind of translate that. I can move it left, right, up, and down all that I want to. It might make sense to translate it to 0, 0, so that your initial point is at 0, 0, because it might then make some of the things we do later on with vectors, the calculations we do with them might be easier if they start at 0, 0. Okay? But you don't have to. On Friday, then, we said, all right, if that's vector U, let me just put a series of vectors over here in the second quadrant. Well, let me get rid of that. So that's vector U. Let's call this vector, I'm going to call that V. Let's make another one here. Names on these real quick. All right, so V and W. And we said, well, let's start adding vectors together. Okay, and we'll just kind of do U plus V first. So U plus V. And what we said is, and you can do this anywhere you want to. Okay, you can move all of these around. Usually the kind of normal procedures to start at 0, 0 with one of them. So I put 0, 0 as my starting point for vector U. And I'm going to see what U plus V looks like. Okay, U plus V. So vector U plus vector V. We need then to put these, we said on Friday, tip to tail. We don't want to start here, okay, because those are tail to tail, okay. We want basically an initial point and a terminal point to coincide. And right now I've got two initial points coinciding, right? So when I put them tip to tail, there is an initial point and a terminal point coinciding, okay? And I get U, so I travel down U and then travel down V. That would be exactly the same as traveling that red vector. And we called that red vector the resultant, right? Okay. So here's kind of the logic behind what's going on here. We could put somebody in a rolly chair. This is how we talked about it the other day, and you can extend this concept really to any type of force that's being applied to something. I think it's just easier for you to visualize somebody sitting in a rolly chair. And I put them at 0, 0. And I say, okay, we're going to clear out a room. Maybe we do this in the gymnasium. We're going to put them right in the middle of the floor in the gymnasium and say, okay, we're going to apply, okay, and we set up a grid in the gymnasium, okay, so we know directions and stuff like that. But we're going to apply a force of 4.24 newtons at a 45-degree angle to this person in the roller chair. Whether we push them or pull them, it doesn't matter. But once we apply that force in that direction, they're going to travel that vector U. Does that make sense? And once they travel that and they come to a rest, they will be sitting at the point B right here. Is that okay? All right. Now the next thing we're going to do is we're going to say we are then going to apply a force of 2.24 newtons at an angle of 116.57 degrees to that person in the roller chair. And once we apply that force in that direction, they're going to come to a rest at point D. Does that make sense? Okay. And that's fine, that's great, that's awesome. All right. But then we go back and say, okay, we should have been able to get to point D maybe a little bit more efficiently. Okay. If I say I want to start at A and go to D down the red vector, it would be using an angle of 68.2 degrees. Okay, so we're seeing that angle right there. And it would be with a length of 5.39. Okay, is that length along the red vector more efficient than the purple vectors? Yeah, okay, 5.39 is less than obviously the 6.5 that we get by going down AC and then CD. Okay, so we should be able to push the person from 0, 0 at a 68.2 degree angle or direction with 5.39 newtons and get them to be at the exact same spot that we use or that we determined going through the purple vector. Okay, so that resultant is a more efficient, more useful course to take. Does that make sense? All right. In all vector addition is kind of predicated off that. Okay, it's the same concept all the time. Now the question is, does this matter? If I flip-flop U plus V and V plus U, does that matter? Well, V plus U, if we're going to say that we had to start with V at 0, 0, and then add U to that to get tip to tail, and I put in this second vector, or I guess third vector, this resultant, is that resultant still the exact same resultant? And my argument is, yes, it is, because its length is still 5.39, and its direction still should be 68.2 degrees. And it is. Even though I applied the two vectors in a different order, I still get the same result. So it's the same sum ultimately. Okay? And that's nice because with our real numbers and even our complex numbers, that we know that addition is commutative, right? If I give you 2 plus 5 and ask you, is that the same thing as 5 plus 2? Everybody should say with a resounding yes, right? Okay. So what we've learned algebraically about our real numbers now carries over to vectors. Okay, well, it's vector addition. We say vector addition is commutative. Okay, it does not matter the order. It is also, we can kind of piggyback this and say, well, if I do u plus v, okay, now add w to it. U plus v plus w. I should be able to just take w. Oh, I've messed up the creation of w. For some reason, I don't know how to fix it. When I create a vector, you create a vector, and if you ever create your initial point in GeoGebra on one of the axes, it will force it to stay there, okay? And you can't drag it. So let's say I want that to be w. I have to create it so it's not starting on one of the axes. All right, so if I go u plus v plus w, it'd be just making sure that we put them all tip to tail like that. Okay, and now the resultant would be from the first initial point to your last terminal point, and that would be your resultant. That would be u plus v plus w. Now, when we piggyback them off that way and look at them with three of them summed together like this and look just at the resultant, that can be kind of confusing sometimes. So this is the way I'm going to kind of approach this. If I do, let's see here, let's move that w back. U plus v should look like that vector right there, right? Okay. So now that I got u plus v, I'm going to hide these. And this is now the vector u plus v. If I tag w on the end of it, does it look now just like two vectors being added together? And two vectors that are tip to tail. And when I do that then, two vectors tip to tail, and look at that vector right there, that should be u plus v plus w. So what's that tell me? The way I kind of viewed it that way, I did u plus v first, right? I did that addition first. I can associate those two, do that addition first, and then tack onto a w, and I should get that resultant from A to F as being u plus v plus w. Now, that's kind of introducing the associative property. Let's see if the associative property kind of works in the manner that we think it should. And the way that we think it should be something like this. We should be able to do that, shouldn't we? Take v plus w first, and then see if we still get, once we add u to it, the same resultant. So here's the resultant. I'm just going to cut and paste this, put it over to the side. Let me change the color. I'll just change the style. That is the resultant we should get. That is the final resultant. So let's see if when we go through looking at, and I accidentally just deleted them. So let's see here. There we go. So we got our three purple vectors here. Let's do v plus w first. Okay, so I'm going to put v down here first, then add w to it. Okay, so that resultant of v plus w should give me that. Does that make sense? Okay, so now let's hide v and w. All right, so this is v plus w. Now if I tack on u to that, okay, tack on u to that, is that resultant, the exact same thing as that one. That kind of makes sense? Okay. So what that allows us to do is say that the associative property does exist for vector addition. Okay. Does anybody have questions over there? All right. It does get a little fuzzy, I think, when you, at least as I've experienced in the past with students, when I start asking you to take multiple vectors and add them together, okay, they don't see the parallelogram that we need to be using here, okay? And the reason is because there's actually two parallelograms that you're using, all right? But we can go from my first initial point, to my last terminal point, and that's my resultant. Okay? All right. We can do, if vector addition works, and I add the same thing over and over and over again, so let's say that I take u plus u plus u, and if vector addition works, then repetitive addition is the same thing as what? Multiplication, isn't it? So shouldn't I be able to take some scalar of 3, apply it to u, and get what 3u looks like? Okay. So if I take u and cut and paste it 3 times, so there's u, and actually let me just do it, start there at 2, 0. Put on another u, tip to tail, and then another u, tip to tail. So that's what 3u would look like. Is that okay with everybody? Now, GeoGebra allows me to do something a little bit useful. I can type in what 3 times u looks like, and it will actually set it in there. Okay? Does that look exactly like what we've got here in purple? Just shift it over, right? Okay, and we can do that. We can make it's got the same direction, and it's the same magnitude. We're good to go. Okay? So we can do what we call scalar multiplication for vectors. You can take any one of these and double them and triple them. You can take, you know, let's look at what one half of u would look like, right? This thing is u, then that red vector there is half of u. Okay? Let's see here. One thing we have not talked about is vector subtraction. Let's go u minus v. U minus v. And in order to apply this and to do vector subtraction, we need to understand what the definition of subtraction is. What did we define subtraction like the first day of Algebra 1? Adding the opposite. So this is actually u plus the opposite of v. And now we have to think about what the opposite of a vector looks like. Okay? So let me put a vector in here real quick. And I'm going to call this one v. So if I got vector v there, let's see what the opposite of v would look like. Okay, so this one here is the opposite of v. And what do you notice? Or to put them on top of one another, they're the same vector, right? But what is different? Opposite directions. Okay? So whenever you want to do vector subtraction, you first have to think about, okay, what is the vector that I am subtracting? And I need to change its direction. Okay? So if I've got a series of vectors here, let's just do u to be that vector there, and let's do v to be that vector there, and I think that's going to be, yep, screwed it up again. All right, let's let v be that vector. Okay, and I want to go u minus v. Okay, u minus v. Well, the first thing you have to do is take that vector and find out what its opposite looks like. Okay, so would you guys agree that the opposite of that would be starting at D, but now moving towards C? Okay, so now that didn't work the way I want it to either. Let me do this. All right, so this would be the opposite of V, right? The same length, but moving in a different direction. So then I go U, okay, and I add to it the opposite of V. So that's the opposite of V. Now the resultant then becomes that vector there. That then would be U minus V. And if I just ask it to do U minus V, you see that it did highlight that exact vector that we came up with. Okay. I think maybe you guys have done vector stuff in physics, and maybe you had graph paper, you did it by hand. I think messing around with GeoGebra's vector stuff is a lot more insightful, because you can kind of play around with it and see, what you think you're going to get, and then you can type it in. If I'm looking for U plus V, I can graph it and drag things around and move it and manipulate the way I think I'm going to get it, and then type in U plus V, and it automatically does that vector addition. Does that make sense? So you can see whether what you've done matches up to the actual answer. Can we do that kind of stuff? That's pretty straightforward, pretty easy. So what they get you to do in your homework, if you start looking at that this evening, which I do suggest, they're going to put, a series of vectors. Usually they just kind of originate a bunch of them here at 0, 0, so they might do something like that. And they might say, okay, find 2a minus v plus w. Okay? And they ask you then to check the box that has the correct graph of that in it. Okay? My suggestion is maybe get some graph paper and draw the pictures. If you keep straight in your head, that's fine, and just kind of visualize it from Levisine's pictures. But you're going to be asked to do this process several times in that homework. Okay? Now, that being said, we've got now the geometric concept, the geometric understanding, hopefully. When we want to apply vectors in the real world and use them to demonstrate some natural phenomenon, we don't want to have to draw the geometry every single time, because that can be a pain in the butt. So we see if there is a correlation to anything that we can do algebraically. Okay? And there is. And the number one thing that we need to understand is that every single vector that you draw, let me see here real quick. Okay, if I take that red vector, okay, that red vector can be broken down or can be viewed as a resultant of two other vectors, right? And those two other vectors we call a horizontal vector or horizontal component and a vertical vector or vertical component, okay? Every single vector you draw, every single vector you can ever imagine, unless they're already vertical or horizontal themselves, because then it's really easy, is some combination of a horizontal and vertical vector. That being said, every single resultant is a hypotenuse of a right triangle. Does that make sense? Okay. And if we start moving this around, the way I kind of set that up, you can see that that right triangle is always going to exist, right? Okay, no matter where that resultant is in the coordinate plane, no matter what its direction is. Therefore, when we're trying to describe algebraically what that red vector is, we do it with respect to what these horizontal and vertical components are. Okay, so if this is vector, let's just call it vector u. Okay, we call this, usually they call it a sub 1. Okay, in this they call a sub 2. Okay, but a sub 1 is the horizontal vector that u is going to be described by. And a sub 2 is the vertical vector that u is going to be described by. And the way we do this is we say that u, vector u, is equal to, now we use these angled brackets, okay? Then we go a sub 1, which is the horizontal component, comma, a sub 2, which is the vertical component, and then we finish it off with those brackets, okay? Now, what's nice is that those components should be a little bit easier than, or easy to deal with in regards to finding their length, okay? Because they're horizontal and vertical distances, right? So if I want to find this horizontal distance, I simply take that value and that value of my, basically the x values of this blue vector, and you subtract them. Okay, so 12 minus 2, right? And that will give me 10. And then to find the vertical component, you take this y value and remove from it that y value. So 12 minus 4, so I get 8. So I would call vector u algebraically 10, 8. Okay? And you see over there on the left-hand side in that algebra pane on GeoGebra, it's calling it 10, 8. It uses a different type of notation. It's more of a matrix notation right here, which is nice because with vectors, we do a lot of stuff with matrices. So having that ability to write it as a matrix is nice. It's a or 1x2 matrix. Is that okay? All right. Generally speaking, your vector u is found by taking x sub 2 minus x sub 1, comma y sub 2 minus y sub 1, where x2, y2 is your terminal point, x1 and y1 is your initial point, okay? And that's important. You always go terminal point minus initial point so that your direction is calculated correctly. So you got the right pluses and minuses with your components. Does that make sense? A lot of geometry here that's analogous to what you have done in Algebra 1. Okay, finding distances, what you did in geometry, finding distances, Pythagorean theorem, that sort of stuff. All right, so if that's the case, when I want to talk about whether two vectors are equal using algebra, it's going to say that if vector u is equal to a1, comma a2, and vector v is equal to b1, comma b2, so if that, then vector u is equal to vector v if and only if a1 equals b1 and A2 equals B2. Okay? Meaning, as long as these ordered pairs are the same, or I don't call them ordered pairs, but as long as those kind of vector matrices are the same, then the vectors are the same. So if I have a vector that is 2, 3, they're represented by 2, 3, and I have another vector that is represented by 2, 3, those two vectors are the same vector, right? Okay. Now, they may be positioned completely different in the coordinate plane. One might be starting at 0, 0, the other one might be up in the third quadrant somewhere, or down in the third quadrant somewhere. But if they both have the same horizontal component and the same vertical component, they're the same vector. Is that okay? So what's nice about that, guys, is this should allow us, let me just hide this stuff real quick, to take maybe that vector there, okay, which we said that vector was represented by 10, 8. And let's put another vector in here. Let's go put that vector. And in that vector, let's think about its components. Call this vector V, which would be the x is what? 4? It's 12 to 16. And then the y value is also 4, isn't it? Okay. So if I do, and the y value is at going up or down? Down, right? So it's, so remember I said y2 minus y1. It'd have to be 6 minus 10. So that should be a negative 4 there. If I were to do u plus v, we know what that should look like algebraically. Or sorry, geometrically. Geometrically, we know what it should look like. Should look like that. That's the resultant, isn't it? That dotted line or dotted vector. We should be able to describe that using these components. U plus v should look like the horizontal component plus the horizontal component, comma, the y component or vertical component plus the vertical component. So 8 plus negative 4. And that turns into what? 14, comma 4. So I should be able to look at this vector right here, and it'd be 14 units to the right, and then up 4. And if I look at the algebra, it's 14, 4, right? Does that kind of make sense? So when I want to do vector addition, all I have to do, if u is equal to a1, a2, and v is equal to b1, b2, then u plus v is equal to a1 plus b1, comma, a2 plus b2. I just add the horizontal components, add the horizontal components, and add the vertical components. And it's subtraction because it's adding the opposite is the exact same way. Is that doable? Okay, so another object that we're allowed to do, if that's the case, think about this, and this would be kind of the proof of this property. If u is equal to a1, a2, then u plus u plus u would equal a1 plus a1 plus a1, comma, a2 plus a2 plus a2, wouldn't it? How many a1s do you have there? So you have 3 a1s, comma, 3 a2s, right? What would u plus u plus u, what could we write that as? 3u, okay? So The argument then is, and you can kind of, maybe the direct proof of this would be using some different components here so that this 3 can change. But regardless of how many u's I want to put together, if I put 4 in there, what do you think this number would turn into right here? 4. Okay? So if I did this like C times, I would have C times U, right? And then each one of these would be C times A1, and then C times A2. So we have that what we call scalar multiplication for vectors. If I want to take a vector and multiply by 3 or 4 or 5, whatever, or even a half, doesn't matter. C is just going to be a real number. Okay? Then all I do is I multiply the horizontal component by that C value, that scalar, and I multiply the vertical component by it. And that will yield then what that final resultant looks like by scalar multiplication. Is that okay? So, kind of these are the ideas, let's see here, that we've just discussed. Basically that, we got vector addition, we got vector subtraction, okay? And then we got scalar multiplication, okay? And those things you can translate to the coordinate plane and recognize those. That's that figure 11 up there is trying to do a little bit with vector addition. I think it's a little bit easier to see in GeoGebra as it's a little bit more dynamic. But that incorporates questions like this, and they say, okay, if we have U, which is the vector 2 comma negative 3, okay, so hopefully maybe you can visualize what that would look like, okay, and then V is equal to negative 1 comma 2, may have a visual image of what that looks like, or go to GeoGebra and graph them both, and then we have this series of questions, U plus V, U minus V, 2U, negative 3V, and 2U plus 3V, and I have all those questions. I don't want to have to graph those. I don't want to have to create a new graph for those 4 or 5 different questions. I would like to be able to just do the algebra. Okay? If I want to do U plus V, 2 plus negative 1, gives me that 1. Negative 3 plus 2 gives me that negative 1. And I've done that vector addition. I've done that tip-to-tail thing with those 2 vectors. That makes sense? Okay. If I want to do subtraction, I don't want to have to go graph this again. This is what V looks like. Let's change its direction, get negative V, and now add U and negative V together. I simply want to take that 2 minus that negative 1 and get that 3 right there. I want to take that negative 3 minus that 2 and get that negative 5, and that gives me my result. Okay? And the same thing that happens with the multiplication with those vectors. Is that okay? So the algebra hopefully kind of expedites the process of finding resultants, and it bypasses the tip-to-tail procedure. These are all the properties then that exist. Okay, U plus V equals V plus U. All that is a commutative property. Okay, or you can maybe you can look at that and say that the symmetric property of addition, or subtraction, symmetric property of equality exists for vector addition. Okay, so it doesn't matter the order that I add them. I'm going to get the same thing, right? Which is ultimately the commutative property. That second one, that's the associative property, right? We talked about that. You can take V plus W and add those together first, and then add U to it. Or you can add U and V together first, and then tack on W, and you still get the same results. Okay? U plus 0 equals U. All that is the additive identity for vector addition. Okay? So if I take some vector U and I add the 0 vector to it, I should still get should still get U, the original vector. Adding the 0 vector is a horizontal component of 0 and a vertical component of 0, so it doesn't do anything to it. Okay, but we need that 0 vector to be part of our vector fields for a lot of our algebra work. And one of those things that we need it for is because if I take u plus the opposite u, I should get a zero vector, right? Okay. This here, this property stems directly from that top one. Subtract u from both sides, right? Okay. And I need u minus u, or u, okay, u minus u, or u plus the opposite u is equal to 0. The length of a vector, okay, this is just something that might be useful if you want to stay away from really large numbers. Let's say I want to find like 3u, okay, or the length of 3u. Well, then it's simply taking the absolute value of the 3 multiplied then by the magnitude of u. Okay. So let's say that I have, see how this property would be useful. Let's say that our vector is 2 comma, let's just do it this way, 3 comma 4. And the magnitude, so that's u. Okay. Let's say I want to find like 17u. Okay. Well, what I could do is take 3 times 17. So what's 3 times 17 give me? Say again? 51. Okay. And now what's 17 times 4? 68. Okay. I could do, so that could be A, 1, and that, or A, let's call that B. And then to find the magnitude of 17u, I would take the square root of 51 squared plus 68 squared, right? Okay. Well, that's kind of a pain in the butt. Those numbers are really large. Okay. The better thing to do is to say that the magnitude of 17u is equivalent to the absolute value of 17 times the magnitude then of u. So the magnitude of u, what's the magnitude there of u? That'd be 5, right? 3 squared plus 4 squared, I need the square root. So I get 5, okay, put it this way, times the absolute value of 17. What's the absolute value of 17? 17, what's 17 times 5? Okay, that's a little bit easier to do in your head than this is, isn't it? But if I take this over here, (51 squared plus 68 squared) gives me that number right there. Take that and raise it to the 1/2 power. Gives me 85. Okay. Multiplication properties that are useful. Okay. What's this property here? Distributive property. Okay. So the distributive property for vectors works. The bottom one, I guess next is also the distributive property, but it's now we've got two scalars being added together. And before we multiply by the vector, you can distribute the vector through. Okay. So this is distributing a scalar through. This is distributing a vector through. But still works. So this is saying that's the commutative property of multiplication, isn't it? C du is equal to C times the quantity du. I guess what they've got going on here maybe is the commutative and the associative property. Start moving the D and the C around over there. That works. We got the identity of multiplication. Okay. We got the zero property. The product of vector times 0 is 0. Okay. And the scalar multiplier of the 0 vector. So 3 times 0 gives me 0. So all those properties work. And as you guys get through other higher level math courses, you'll realize that those have to exist for us to view vectors the way we need them to work or want them to work. Okay. A lot of times, because right now we're dealing with what we call vector addition, vector subtraction, vector multiplication. And we want to kind of draw a bridge between the addition, subtraction, multiplication, and that kind of stuff that we normally deal with. Okay. With our real numbers. Okay. called rings and fields and stuff like that. It's kind of a pain in the butt, abstract algebra. But we need those properties to exist for some of the things that we do here in a little bit. There is an assignment on WebAssign. There should be. I want to check, make sure I've opened it. We do on Wednesday. I'm going to open a couple more. Okay, probably have maybe a total of 3 assignments this week, probably. Tomorrow we'll start talking about the fact that every single vector you ever draw can actually be broken down to unit vectors.